you worry about a thing. We have a red pencil. Hello world, my name is Alan. We're doing LeetCode live practice. And for today, we picked, I've been practicing this matrix problems. And for today, we have the problem Game of Life, number 289. So the clock is ticking. We're live. Hope I'm sharing. And according to a Wikipedia's article, the Game of Life, also simply known as life, is a cellular This is tons of new words I don't understand, but the board is made up of, okay, it looks like there's like follow-ups. Let's see if we can understand the problem. I mean, what the problem is looking for in the next 10 minutes. Okay, we have a grid. Each cell has initial state life represented by A1. Or the live, yeah, this is live or leave. Yeah, live or dead, represented by 0. Each cell interacts with its 8 neighbors. Do I need to read that article? That's what I'm curious. Conway Gamer. Okay. Cellular automat. I don't know. I don't know how to pronounce this word. So, anyways, okay. So far, it's one and two is okay. Live or dead. That's Each cell interacts with its 8 neighbors. 8. Yeah, including 4 diagonals. I see. Using the following 4 rules taken from the above Wikipedia article. Okay, all right. I like games, any alive cell with fewer than 2 live neighbors dies as if caused by underpopulation. Okay, so fewer than 2 live neighbors. So like this one fewer, okay. Any live cell with 2 or 3 live neighbor lives on to the next generation. So if there is 2, at least 2, okay, 2 or 3. Okay, any live cell with more than 3 live neighbors wait a second. Overpopulation. Live cell with more than 3 live neighbors dies as if by okay, if there is like 4, 5 or whatever, like more than 3 would be, which one is more than 3? Which one is more than 3? Any more than 3? I need my red pencil. More than 3. Do we have an example? I don't think we have an example. 3. Okay, there's no example for 3. for more than 3. All right, that's fine. I don't see it. Okay, with more than 3. Okay, so I need that logic. So less than 2 dies. 2 or 3 leaves. And then more than 3 dies. With exactly 3 live neighbors becomes life as if by reproduction. With exactly 3 lives. Okay, if it's 3, become live. And the next state is created by applying the above rules simultaneously to every cell in the current state, where births and deaths occur simultaneously. Given the current state, return the next state. Okay, so we just need to do one transformation to produce, yeah, and there are follow-ups. Okay, so one transformation in this example, one died, it had only less than 2 neighbors. Then this one had 3, 1, 2, 3, so that revives, or what's the word? Yeah, became live. Then no. This one has less than 2 dies. This this one had 3. So no, this one dies, this one revives. Is that the word? Revive? Revive meaning, what is... They call it births. They call it births, yeah, but yeah, revive, to take up again, renew, to activate, set in motion, restore, reactivate, to restore to life. Yeah, revive is probably the word, yeah. Anyway, so revives. Okay, what is... Okay, we're within 10 minutes to kind of at least read. Okay, in this case, what happens here? They each have 3 neighbors. Why would they each have 3 neighbors? What's happening? Okay, so yeah, this one revives. Oh no, they have 2 neighbors. Yeah, I'm a little bit so this has 2 neighbors. These have 2 neighbors, so they stay and 1 revives. Got it. Got it. Okay, the problem as I see it now is when we want to update, and it would be easy to do if we could do it in one action, or if we could like mark the one that needs the change first, and then in the second do the change. Yeah, mark what needs to be updated first, and then do the change. Can you solve it in place? Yeah, remember that the board needs to be updated simultaneously. You cannot update some cells first and then use their updated values to update other cells. Yeah, use their updated values. That's what we don't want to do. We represent the board using 2x2 array. In principle, the board is infinite, which would cause problems when the active area encroaches upon the border of the array. That is, live cells reach the border. How would you address these problems? Sheesh. Okay, the board is up to 25 by 25. And by 25. It's 1 or 2 in this question. These are follow-up questions, but can we do it without the follow-up, without making it harder? Essentially, we just need to in place. Well, I guess when they say in place, they mean without using extra memory, because, yeah, you could, make the updated copy and then take that copy to the board. Yeah, copy that updated clone and then copy that values from the clone to the board. But they are saying, I guess they're saying, can you do it without? Jeez. So how can you mark? I need to take my. How can you mark the new state without messing up the values? Yeah, updated values to update other cells. Yeah, so well, since they're only zeros and ones, you can use some other numbers to mark what needs to be so that what should become a 1 essentially just mark those that needs to be ones. Just go following that rule, just say, okay, this and something needs to be 1, something needs to become zeros, need to become so we could just use some other numbers, like I don't know, to mark the, let's say we could use now they have just 10 for dead and 11 for live. So, but the problem is, if we change, okay, let's say we change this. We know this one needs to become live. We put 11. And then we go to its neighbor, check it out, and we need that value. We need the old value. So we need the new value and the old value. Or we could also do other thing, like mark values as those that need to be swapped, that need change. Yeah, because how can you mark them? The values that need the change. the values that need the change. Because you could have like 25 by 25. Can you have like, let me draw a little bit. So Well, that example 3 by 4, right? So could we mark things? Because you see the coordinates of those that need to be changed. We can write them. Yeah, we can write them in just as an array. Save them like this needs to be changed, this and this and this. Dated. Could be like a list. It could be a list of hundreds, or I don't know, 20 by 20, 25 by 25. I'm also thinking, am I making this problem harder than it needs to be? Because when they say in place, well, because if we use any extra memory, that's like not really in place. Which could happen when the active area encroaches. Encroaches. Okay, so it like attacks upon the border of the array, which address these problems. When the active area I don't think I understand the second question. What is the problem? Meaning like you will have less just live cells reach the border. What's the problem with that? What is the problem with live cells? Given the current state, return the next state. So yeah, just the next one state. It's not like a series of Yeah, essentially, yeah, we could either use some memory and then it's pretty clear. If we try not to use extra memory, which is, I guess, what they mean here, matrix simulation. But then that's what I'm trying to figure out. Yeah. Because it's too simple when we use some memory. Just go based on these rules and yeah, write down cells that need to be updated. I mean it, and but I don't know if we need. It sounds too simple, although it's kind of, yeah, you do need to go around, count all this, check the neighbors, count. Yeah, like there's these rules. Yeah, now try not to stay within the boundary. You got to stay within, yeah, and all that, but that's pretty trivial. How do you do that without extra memory? Well, then you would need to use some kind of mark them somehow. Yeah, like mark that. Like this was a 1, and now it needs to become a, I don't know, 0. It was a 0, now it needs to become a 1. And stuff like that. Yeah. So that, yeah, so we can recognize it, what is in the first state and what it's be in the next state. Yeah. They are 0, they are numbers though. So you can't use like 01, but yes, you can use like 101. Yeah. So or just any other number, like let's say 3 switch to 0, or yeah. So we know that that was a 1. And 4, so like kill, revive. Yeah. And yeah, so we know that revive means it was 0, now it turned it to 1. Yes, I think like that. Yeah, 1 turned to 0. So as we go, we will just use that logic. Yeah, I think it's that's kind of the solution for the if you see a 3, that means it's still a 1. You can even like use like modulo by 2, okay, to know what it is now. Like if x, if it's 1, which will happen for 2 and 1, yeah, then it's now 1, yeah. Then the same thing. Yeah, to know what it's now, what it's currently. Yeah, whatever. But or you can just do this code. Yeah. Or yeah, why do we even need to go to 4? We can go to 2 revive, 3 kill. Yeah. So yeah, basically like that. So we don't need to go over the matrix anyway. For row is range board. For column is range board 0. And board row column is our value. Now we need that mechanism to to count the neighbors. Count those neighbors. Should we write a separate function for that? Because we need to check. Neighbor. So let's say neighbors. If I knew how to spell neighbors. Okay, neighbors. Count neighbors. It's going to be a function that's going to take row and column, these integers, and it's going to take the board, obviously. It's just the board. Yeah, so this function count neighbors. Is going to return integer. Yeah. By the way, when we count it, then we're gonna change it depending on But let's say neighbors all have already been updated based on this rule. So we'll see, we'll look at the neighbor. For each neighbor, there is a rule. I mean, to recognize what it is, 0 or 1. Essentially, we just say that board, this RC divided by 2. Whatever, if it's 1, if it's 0, that's how we know what it was. And so we just need to count is 0, then we say count plus that thing, whatever that thing, now we need to iterate over those. We need to go around these 8 neighbors and call them by their coordinates. But before we call them, we need to make sure they are within the, not out of range. So we have row and column. And neighbor row, neighbor column, and well, the simple way is to say, okay, if a row is more than 0, so it's not the first row, we can check the upper neighbors. At least those that are above and to the right. Yeah, then we're gonna say count. Yeah, count. So we're gonna say row -1, and we're gonna say row -1, column +1. Also, if column is more than 0, yeah, so that diagonal neighbor, it has 2 requirements, yeah. If column is more than 0, we can check the neighbor to the left. Yeah, so let me just mark the neighbors that I'm checking. So we're going here, that's the target. So the one at the top and to the left, we're got them. Now the one at the top and to the right we got, to the left we did. Now we have, yeah. So now I have that. Let's go I don't know if we can go clockwise. So, but also if we are at, we know we are not on the first row. We know we're not on the first column. So since we're not on the first column, we can check the same row, the previous column. Yeah, so to the left, we can also check. Because in that position, we know, oh, but we need to check that also outside of that position. So essentially, we need, yeah, not only there, we need to check. So we do need that extra, yeah, if column more than 0, yeah, we need to check, yeah, all of the columns to the right. It's, yeah, then, so we done that. We did that. Then we need to go, yeah. If row is less than length of board -1, so it's not on the right. And we also can check the to the right. And now there are those at the bottom to the right. Oh, wait a second. We can't check that unless we know that condition is true. Yeah, so we need to, yeah, say if, yeah. Now I think we're a bit more consistent, because I was like, I think we're missing something. I mean, we could just write them all like separately. It might even like if R is more than 0 and yeah. Yeah, just separate them, because yeah, each direction have its own check. And they're pretty clear conditions. So yeah, so there's not like, yeah, this, if, yeah, this corner, yeah, now we can actually like do that clockwise if we need to. I don't know if we actually need to worry about it. Because yeah, so at the top, we check at the top. Now the one to the top and to the right would be this one. No. No, that will be, wait a second, that's to the top and to the right. Yeah. So, yeah. Now, like 3 o'clock would be the one that's absolutely to the right, will be this one. Now we have 3 o'clock. Yeah, we just add the row. Now, if we know we are at the, that's the last one, I think. Yeah, that's the corner one. If we know so we got the 3 o'clock now, this diagonal. If we know right is less, row is less than the end, and column, by the way, that's column. Yeah, that's, wait a second. Yeah, by the way, these are rows and columns. So let's start over. The first one, we're checking if we're not in the top row. We're not. We can safely take one, go to the higher row. Okay. Now, can we go to the higher row and move also by column to the right? We need to make sure, that the column is not at the end of the board. Length of the board -1. Yeah, and we can actually say that, the length, this rows is length of the board. Yeah, calls is length of the board. 0. So yeah, so we just calls. Yeah, I guess playing with these coordinates is quite an exercise in itself. Yeah, so row, if now, okay, we got the 12 o'clock, one to the right, and to the up and to the right. Now we need to go to the right. So rows, we hope we're not at the end of the rows. Oh, that's columns. That's what I confused. Yeah, so whatever the row is, just go to the next column. Okay. Now this, if it's not the last row, and not the last columns, then we can go, to the, now we could go to also, if, go 6 o'clock, if columns is less than calls, and we could go columns, wait a second, 6 o'clock is rows. We could say, okay, give me one more row, next row, the row below. And if now the final one, is it the final? Wait a second, we got that, row below, and then, wait a second, so 1, 2, 3, 4, 5, 6, it's far from 1, 2, 3, 4, 5. Yeah, so this 5. So this is one at the top, this is one below. Now we need to check the one, if row is less than rows, and column is more than 0, then we can do the check for next row, column -1. Yeah, so that gives us that. And then we need to check if the column is not 0. If column is not 0, we just check the left one. By the way, and if both, so column and row not 0, we can go. Okay, I think these are all the conditions. The problem is, this is like, some of them are more general, and they will, like this one, or like this one will count 1. So will count several times. So we need a switch case. We need a switch, and we need cases for all these. And it will look much, much shorter, yeah. Case, oh, oops, case that. Yeah, so all these cases. I mean, we could just do it like that, but it doesn't really matter. Mm-hmm. Mm-hmm. Oh. Oops. And then we have, yeah, I could have, yeah, we need one of them only, the trigger only one, not a group. Mm-hmm. Don't you worry about a thing. Mm-hmm. Mm-hmm. Okay, so we'll. Mm-hmm. We should have 1, 2, 3, 4, 5, 6, 7, 8 cases. Yeah. So that's our function to count the neighbors. And now we know the number of neighbors. We could have, so once we know the number of neighbors, we'll also have a switch. Because depending on the number of neighbors, we can just do this, count neighbors. Oh, case. Oh no, we need the neighbors. Does it depend? Well, well, yeah. So there are several cases like that. These are the cases, yeah. Yeah, so we do need to do these cases, yeah. Case neighbors. If it's less than 2. Then that position is gonna be kill. We need to kill them. And by the way, if it's less than 2, we kill. If it's 2 or 3, doesn't change. More than 2 also kill. So if neighbors is less or neighbors more than 3, yeah, and this happens, yeah. If so those are the the kill cases. Leaves doesn't change. Two or three leaves. So essentially, yeah, but if it's exactly 3, if it's 3, then they leave. Well, we can check what there are, but essentially, if it's 3 neighbors, they're gonna either leave or revive. It doesn't matter. Yeah. So, oh, wait a second. Wait a minute. 0 is dead. Ouchie. 1 is alive. Think our math. Yeah, we wanted to kill. We messed up. Yeah, so yeah, we need to mark them. So 0 dead, 1 live. So 1 means live. So we need to say that 2 means kill, yeah. So we need to do the opposite. Yeah, so if it's so if it's 3, then we are reviving it. Wait a second. No. The logic is we need to discern the differences here. Yeah, if we see a 1, that means it's live. We count it as a neighbor. If we see a 2, oh, that's why we wanted to kill at 3. Oh, okay, now I see. Okay, so it's the other way around. Yeah. So, yeah. So 3 means kill. But in this check, yeah, so that's why 3 will trigger, it means it was 1 anyway. So this neighbor was live. Yeah. The neighbor was live. We could do if it was 1, it was live, or if it's 3, it's still gonna add 1. If it was dead, or we were going to revive it with 2, it's gonna be 0. So was anyways, it was dead. Now, if it needs to be killed, we set it to 3. If it needs to be 2 or 3, it just leaves. It doesn't matter at all. If it's yeah, revive. Yeah, if case neighbor is 3, we need to revive it. So that's revive. Yeah. Otherwise, we just don't change it if it's. Okay, so that's how we we got the neighbors. We updated these values in place. Now we need to go over them again. And and switch again, switch. Yeah, depending on what we see, we need to update them. Yeah. If well, it's essentially it's switch board row column. Well, if it's yeah, we only need to do the change if it's like 2 or 3. Case 2. Case 2. I need to. Case 3 kill, case 2 revive. That's kind of it. Oh, so yeah, there is no NR and C neighbors. We just use the C and R. Yeah, so NR is R. And C is C. Jeez. I might have messed up with a lot of missing return. Oh, we need to return something here. Return count. This is like an hour. Okay, out of range. Why? Oh, because the last one, well, if it's smaller, calls is not it's -1, yeah. Length -1 is the number of columns, yeah. Okay, so, well, we've reached the hour of an hour stream. And I think we're close. I'm just, for some reason, we're getting all the zeros in our output. Neighbors, smaller than 2 or bigger than 3. I wonder if we got the number of neighbors right. Oh, I think I see the problem. We need to do these checks separately. Yeah, I mean, these are all different neighbors of 1. These are 8 different neighbors. Oh gosh, yeah, so yeah, of 1, I forgot, man, these are all different neighbors. That's how I got a little, yeah. Of, yeah, let's keep the readability. Yeah. If yeah, they're all different neighbors. I mean, these are checks if we can call them. That's the thing. These are the checks. Okay, we're halfway through. I wonder if this format button will fix these extra things. No, it's not gonna fix these extra spaces like that. Well, this is kind of it, yeah. And something is out of range. Oh, why? Range of 4, length of 4. Rows, columns, yeah, because both of them, rows and columns, are -1, yeah. I mean, essentially, it's not the rows, it's the last row, essentially, what it is. But the last row. Why is it so? What is its problem? Oh, this one worked. This one has a bug. Well, we can find that bug, I guess. And we need to drink some water first. So what's going on here? These are actually the last row, last call. It's what I like is that, like, output. while it runs, but other than that, okay, let's look at the first case. And okay, let's check out the code. Okay, so let's say we got our commands right. So like 2 revive, 3 kill. So if it's 3, if we got a 3, yeah, it's 0. If it's 2, it's 1. But how do we mark them? Okay, so we count the neighbors. If fewer than 2, it dies. If more than 3, it dies. So we mark them as they're now 1, but they need to be killed. So this neighbor will be, as we go, so we have a position, look at its neighbors, all the 1s and the 3s will be treated as 1s, so they need to be killed, but they're now 1s, so in our current state, so that will count as a neighbor. Still alive though. Still alive. And what? I'm just checking. Okay, so that seems right. If neighbors is 3, so we see some value where neighbors is 3. Well, they either 3 neighbors lives on, and if they're dead, they need to be revived. I think that's the problem. We need to, before we don't try to revive. If it was a 1, yeah, we need to check what it is. We don't need to revive something that's not dead. Yeah. If it's, yeah. And yeah, and it's now dead, because that's how it messes it up, I think. Yeah, if it's currently dead, we need to revive it, because when we match, the reviving means it was dead, so it was 0 in the first state, in original state. 2 will count as 0, so it will count as a dead neighbor, while it's actually a live neighbor. So now we stop marking those live deads, lives. So we say, okay, if neighbor is 3 and it's currently dead, then we revive it. If neighbor whatever, otherwise we just don't touch it. Yeah, we don't do anything with it. It's a live neighbor that's gonna stay alive. So what's wrong with it? So output becomes this one is 1. The number of neighbors is less than 2. I think so. Here is what we've like 115 into that problem. And I think we can like do some overview of what we have. In terms of time, because my attention was, we've done some extra work of going back and forth with these ifs. It looks like the general logic and the solutions it looks like we found the logical solution. Just need to see where the bugs are, and if we can make it run eventually. Because and that is our in place solution, change in place. So we can't see if the neighbor count is right. Could have some bugs. We could do some prints for the neighbor count. Neighbors. We want to see the neighbors, and we want to see the RNC, row and column, right? I don't know. Will it help us at all? So this first one is 1. By the way, we need to call the neighbors only when it's like, oh no, we actually need to call for the zeros as well. This has 1 neighbor. That has 2 neighbors. It says it has 2 neighbors. This, so it looks like it. Now, 0, 0, 01, or 2. This does has 2 neighbors, but this one, 01, 01. Probably some bug here. At the top, check the top. Oh, it's not going to check the top. It's not going to check anything at the top. To the right, we get the same row. column plus 1. If we see a 0, we need to see a 3 or 1. 3, that means it was 1. We need to kill it, and 1 is 1. So that's 0. So it's somewhere it finds 2 neighbors. So that should be 1. Now, if rows, so it checks rows plus 1, the same column. Now, if rows but column back, so this is like row higher, column back, which is 0. Row higher, column back. If column, then we'll check the back column. Wait a second. If column is more than 0, yeah, we can check the column, the previous column, same row, 0. And if row and column are not 0, which is not the case, return count. So for this row and column, count starts at 0, which is adding to that count. The board that value, if we modulo divide 1 by 2, so the remainder will be 1. And we don't count the value itself, right? We never accidentally added the value itself. No. If 3 is modulo divided, and by the way, there shouldn't be any 3s before we actually, when we just check this one, this 0 just stays 0. This 1, for some reason, it should be killed, but it stays because the computer thinks it has two neighbors, right? Yeah, so this case for when it's like this row 0 point, yeah. Let me just do print format. Neighbors value row value column value next line. Yeah, so we kind of like see what is what, which is what. Neighbors, yeah, so this row 1 column 2, it thinks neighbors is 2. I'm also curious why this row 1 column 1 neighbors is 7. 1, 2, 3, 4, 5. Nothing. So there is a problem with the function, with the neighbor count. And even initially, when we're just counting, I mean, what would you get if you... I just need to check my common sense. Like, let me see, like, what is 1 modulo divided by 2? It's 1. And what is 3 modulo divided by 2? It's also 1. What is 0 modulo divided by 2? And 1 and 2 modulo divided by 2. They're both zeros. Then what's the problem? What is your problem here then? Why is it adding more? Because we never go to the same neighbor twice. Yeah, we're checking different neighbors here. So yeah, some conditions overlap, but the neighbors are different. And we say that count is incremented by the remainder division of that value by 2. So R, if row is 0 in our case. I mean, what else can we do? We need to like... I just want to see what is, yeah, what... I want to see what count is. So we return the count, which is the neighbors. Yeah, I mean, what else can we do? We need to add that thing to between every, and just check which one adds more. Which check adds more? 8 prints. Yeah, so this first 3 are fine, then there's 1, and then there is, yeah, this, wait a second, 6, 7, 8. So on the 7th, it finds a neighbor. Okay, 7th check. When, well, it says if. So if column is bigger than 0, and okay, if column, so same row, 1 column back, it finds a neighbor here. We were just there. And it looks like we might have added that neighbor. How could we add that neighbor? So we were just there. It only found one neighbor, that's right. So it found like on the third one, yeah. And one neighbor. And apparently it changed something. So, if it's dead, don't try to kill it. Jeez. If it's live, yeah, only then we need to worry about it. I should be working now. Yeah, I'm telling you, it's gonna work now. Yeah. So, should all be working now. With all these prints, it's still pretty fast. Yeah, so this change of state could become pretty confusing. Yeah. I wonder if there is probably like 5. Here is a 5-line solution with like much smarter, much more readable check to all this check, and yeah. Yeah, so we solved it, like, took a bit longer, but it's kind of the practice. Yeah, so let's see the solutions and just see like what people did. No, it's not really 3 lines. It's a good. I'm just checking if there is like super short. Yeah, so they did the movements like that. They did those movements like that. Yeah. Directions. They did the directions, and yeah, they do the directions. Oh, that one. Did they do the directions? So if it's more than 0 and it's less than, and less than columns, and or equal 0. So they decided to count neighbors. That's a sweet idea. Let's just do nested loop. Yeah, instead of checking 8 neighbors, let's check 400 or something like this 500. Everybody go. Well, we're just gonna loop, but then we're gonna check if, yeah, we're gonna do the loop over everything. So 500 iterations. But yeah, if the if that coordinate is one of the neighbors, yeah, check what it is. Yeah. I'm not even looking if they did the follow-up solution or not. I'm not looking at that. I'm just checking like if the length is like if they found something super short. But I guess for the shortness of code, yeah, you could like I could do something like that. Pre-gen, yeah, they use some kind of memory. Game of life. Bit manipulate. Oh, I like those. Those should be bit manipulation, huh? We even got one of those. Nice, nice. Okay, so this is like second. We're into 90 minutes. And I didn't think of bit manipulation. I wonder what they actually do here. They're like shift and Salonish. Use something. Variable. BC is that. What is this? And then they just go do something. Wow. Change in place. Yeah. Okay, directions, count neighbors. Okay, count neighbors. How did they do that? They say -1. They say -2. Okay, if it's -2, -1. Well, when they count neighbors, yeah, they check like if it's less than 0. Oh, wait a second. If. All right. I mean, it looks like everybody's like doing the directions thing in some way. And we might, I guess we could do it a little bit, get it a little shorter than that with those directions. Yeah. Sometimes like this, the fastest way is just to do it as simple as possible. You need this 8 directions and and sometimes they even use like a map of functions. Like this function checks that neighbor, this function checks that neighbor, and then there is this. They just go over these functions, and and it's actually not that long sometimes. Yeah, just like so. Anyways, solved medium level problems. Good practice. Takeaways. Yeah, the recap. The word I was looking for was this interim results. That was what we had earlier. Now we have some results, and I guess the recap. I think we found the logical solution. We a little bit confused ourselves with it because of this state change in place. Yeah. But given how simple our count neighbors is, we were able to like debug it, because we could just like print what's happening, see which one, where the problem is. Because each check has its own 3-4 lines. So we just knew which check, and also having them happening like in clockwise direction also helped, by the way, because we could trace that, trace the problem and see that we're actually, doing, forgot that, we shouldn't be killing what's not, shouldn't be doing some operations. We confused the system. Only those that are in the state that needs to be changed, yes, should be. So that's the recap. And good practice to do it next time in shorter time, to work on the speed. Obviously we could get like, I don't know, 10 minutes faster if we just didn't mess with these ifs for so long. Also, I would fix this. This is not real rows. This is this thing is not really rows, but it's that some row and some column. I'd say this. Otherwise, it's pretty straightforward. I would say it took me some time. I was kind of, what's the word? Swifting. That's not swifting. The opposite of swifting. Sifting through, mendling through these coordinates. Like, okay, we're gonna go up. We're gonna go. So meddling. So that took some time. That's why it's good practice for the matrix problems. And this concludes, I think, our practice with the matrix problems. We actually solved 3 problems today. I think we even solved more, but probably 3, right? Right. We solved valid Sudoku, rotate image, and this game of life. Oh, wait a sec. Set matrix to zeros. Oh, we solved like 4 matrix problems today. Valid Sudoku, rotate image, set matrix zeros, and game of life. Okay. So that concludes the practice with this matrix group. There was another problem that I solved a bit earlier, the spiral matrix. Quite peculiar. It would be good to practice it again. So there are a total 5 problems, and that's good practice. With the matrix problems, we'll come back to them later. The next one will be the problem with intervals. So that's in the next video. Thank you for watching, and hope you see you in the next video. Where is the button? Oh, see ya. Okay.